Recording in.
Excellent. Thanks very much, Musard. Very happy to be here. And in fact, was giving a talk here like around 1 year ago. And after that talk and the discussion with all of you, I immediately thought, oh, this was fantastic. I should try to come back as soon as possible when there's some new fresh results. And that's indeed the case now. So I'm very happy to be here again and share those results. Today's topic is crawling and scanning the web. We'll kind of do a deep dive into how far we can push it, how far we can reach into the web. And for that, we leverage the mechanism of string constraint solvers. This is joint work with Benjamin Eriksson at Chalmers and Philipp Ruemmer's group in Uppsala. Okay, so yeah, we're in the business of web crawling and vulnerability scanning. The web is still not a secure place. A lot of things kind of happening, and the news are full of web attacks that succeed, unfortunately. And one of the interesting ways of dealing with those attacks is essentially black box scanning, right? Sometimes we don't have the source code of the application. We try to scan it in a black box way, look for vulnerabilities, look for any kind of exposure. This is a very active topic. So essentially what you have in this area is practical scanners, some open source, some proprietary, like Arachne and Zap. Yeah, very popular. And then you have a field of research scanners trying to kind of push the boundaries and then introducing new things. For example, the Jack scanner pushes more in the direction of pretending that the scanner is more like a user, trying to find dynamic elements, submit forms, do clicks. So that was a big step forward. Enemy of the state is another approach that focuses on navigation graph, trying to recreate this kind of server-side state from the client-side actions, trying to recreate the navigation graph and aims at traversing it. And recently we had we designed a scanner called Black Widow, which combines the advantages of practitioner scanners and research scanners by doing all of these things. So essentially, yeah, the strength of that is we can pretend we are a user, submitting forms and clicks. We can model the navigation graph, and we can plant injection tokens and look for them in the application. So that way we connect the sources and sinks in a black box fashion. So that's a kind of elegant way of doing it without touching anything in the source code and not looking at it. So that's the state of the art. All is good. So yeah, these tools are used a lot. Unfortunately, they hit a major roadblock. This roadblock is input validation. And this is something that you go to Facebook, that's the first thing actually you see. It's something the scanner gets stuck on. Okay, so what do I mean? Well, yeah, actually, this is from Facebook, where you need to enter valid mobile number or email address. That's how you log in. And if you just provide some random guess of a string, well, you're likely to fail. You'll get stuck at the very first page of Facebook, which is unfortunate because, yeah, I mean, the whole idea was to scan in depth. This is very common. This kind of input forms occur in web applications, and they require certain format of input to be provided. So like here, mobile number or email. Here, moving further, only email. Okay, so phone number wouldn't work. Other cases, username with a constraint that it should be between 6 and 8 characters, all lowercase, right? So again, okay, this is a challenge for a scanner. How do I know that I need to provide that input? So many of them get stuck. Or maybe you don't see here, it says first and last name. So again, another format. So yeah, obviously this is very common on the web to have these forms with input validation. And well, unfortunately, yeah, the state of the art of the scanners cannot do anything without that. The approach practiced so far is essentially have a kind of prepared library of inputs. Like, well, emails are common, so let's try all typical emails, phone numbers. Yeah, so essentially what the scanners have now is library of most commonly used input which they try to use to pass those forms. So essentially, it's kind of guessing approach or brute force approach. And as we'll see in this talk, this is often not sufficient because many of the input validation constraints are a bit more specific than just email address. Okay, so state of the art doesn't quite cut it. So in today's talk, we see quite a lot of regular expressions. So it's going to be, dive into that. So, and kind of what we'll see, essentially how regular expressions are used for validation, what are the security risks, and what we can do about those security risks. So HTML5 introduced an attribute called pattern, which allows to include input validation constraint in, and as part of one of the attributes in a form, in an input tag, right? So you have a form which expects, name, email, type text, so it's some kind of string. And pattern means that, well, this input has to satisfy this regular expression. Okay, so this, if you haven't seen this recently, it might look cryptic, but we will be very, very careful to explain all regular expressions I use in the talk. So essentially, dot means anything, dot star means 0 or more times, okay, in the regular expression notation. So here we are obviously after email, so any character followed by @ then any string, then the dot, which is escaped here with the backslash, and then we have 2 or 3 lowercase letters. Okay, this is the syntax for this regex. Okay, so far so good. So to illustrate, because if you're not used to this notation, so to illustrate this, I'll use these diagrams, which is kind of a nice way to explain it. So I see here, a bunch of characters followed by @ bunch of characters, dot, and then 2 or 3 lowercase letters. So we'll use this diagram quite a lot. So that means that for this particular pattern, so if I provide something like this, then this will not pass input validation because the @ is missing, but this will be perfect fit. However, so we are interested not only in coverage of web applications, but also attacking them through input fields, because this is important class of attacks. Cross-site scripting is done by through injection. So both coverage is good because then we can reach more vulnerabilities, but also direct attacking through the input fields is interesting. So for us, and in fact, this pattern accepts cross-site scripting payload because angle brackets are allowed. Right, so we can arbitrarily insert this. Okay, so that's so it's good to have constraint, but maybe it's not good enough because we can inject attacks here. Okay, so that's what we'll be dealing with today. Okay, so in general, so regular expressions are used quite a lot on the web for this kind of input validation. And if you look at textbook, so maybe you remember, some of the early courses and CS programs, we teach so-called textbook, regex, and then it's about literals, concatenation, alternation, and cleaning star. So this is 0 or more characters. Let's illustrate it here, all super clean and nice. For this kind of expressions, we can do transforms between automata-based models and other language models, all great. But the state of the art on the web is much more complex. So essentially, it's much more beyond textbook regular expressions. So there's an ECMA standard for regular expressions that pushes it to basically mini programming language, which contains lots of features: capture groups, back references, anchors, workarounds, and that's what we need to deal with. If you want to solve those constraints, well, we need to handle the challenge of real-world expressions, regular expressions. For example, this is a common pattern from on real web pages from the wild, which we found with our crawling. This is typical check of a password. Okay, you choose a password, and then the browser tells you immediately, no, this is too weak, right? This is very often implemented by a pattern like this. Okay, and this is not a textbook pattern. It has a bunch of look aheads. Okay, so what is look ahead? So you see the actual pattern is just dot star, so any character. That's what's admitted by the regular expression. So yeah, anything goes, except, so we have this several constraints applied to this regular expression. So the idea with this look-aheads is that we can ask a pattern to be checked without consuming the regular expression. So okay, it's kind of logical condition. So if you look at the first one here, so it says that there should be at least one digit in the password, right? So this is a positive look ahead, says, well, any characters followed by digit. You can also see here, okay? Digits should count. Then the next look ahead is about at least one lowercase letter should be passed in the password. The next one is about at least one uppercase letter. Okay, so these are the three positive look aheads. And then we have a negative look ahead. Okay, so this question mark, exclamation mark says that, well, S is a white space, and this basically says that the password should not contain any white spaces. Okay, so that's negative look ahead. Okay, so yeah, all of a sudden from this nice textbook expressions, we are in this business of dealing with this look aheads. So yeah, that kind of raises the complexity. Okay, but yeah, that's the typical password pattern. So the challenge here is to deal with all those expressions, regular expressions used in input validation. Okay, so far I talked quite a lot about client-side validation, and that's the focus of this talk. But this is an important kind of consideration, as we are in the business of crawling. Okay, so the consideration of client versus server-side input validation. Okay, so in crawling, what we are really interested in is to pass through validation, which is server-side, right? We want to cover as much application as possible. For client-side, we can, in principle, ignore any kind of validation because we can replace JavaScript, we can throw away attributes. We, as a crawler, can do whatever we want on client-side, right? So what we're really interested is, code coverage on server-side. Therefore, the crucial thing to pass is actually server-side validations. Okay, but so there's an interesting insight is that so essentially we have client side of the applications here, server side is here. Here, as I mentioned, HTML5 as attribute is available to do this kind of date check or string check. We also talk about JavaScript validation shortly. And then on server side, essentially we have some framework which also allows regular expressions, right? You see here that, okay, we are kind of asking for, strings of certain characters or decimals or dates. So the insight is that often, essentially, the push in web applications is to make this consistent. So the server side and client side agree. In fact, sometimes we might even have some stronger checks on client side, but just to prevent kind of input to arrive to server side. And in fact, some of the frameworks like Spring MVC and ASP.NET, they actually provide ways of reusing the patterns. So whatever you use on server side is also used on client side. So in this case, essentially these patterns are extracted and used in jQuery validators, exactly the same patterns on client side. So that's a very important observation because of this consistency that is desired. So that's great because then we can focus on client side. That's something we can access from the crawler with the hypothesis that whatever we pass on client side will also pass on server side. Okay, and our observations from the empirical studies confirm that, and evidence from these frameworks, also confirms that they're intended to be consistent. But it's good to keep in mind that it's always, the server side is ultimately is important. Okay, so in this talk we focus on client side, but with the ultimate goal of getting through coverage on the server. Right, so what we would like to achieve, so find a pattern in a web application and compute an input that will allow us to pass through the input validation check. That's one thing, that's for coverage. But also another interesting problem, if you can solve, is that well, if we can check if the pattern is attackable, right? And then we find a pattern, and then we can check, is there a string that includes a payload, right? That also satisfies the pattern. Okay, so these are two separate problems. So this is actually a perfect fit for applying SMT solving. This is exactly what the SMT solvers are doing. Give a constraint, they give you input that solves this constraint. There's nothing we can reuse, in a kind of that's available. So many SMT solvers, they focus on, they don't handle strings. Some do strings, but they don't go anywhere close to the power of regular expressions. That's the ones that I showed you. So for that, essentially, we collaborate with Philipp Ruemmer's group in Uppsala, who helped us to design a special purpose SMT solver, which focuses on this kind of ECMAScript regular expressions. In the talk, I'm not going to say so much about it. It's really their part of the collaboration. But this is the pipeline that we have there. Essentially, it's quite non-trivial. And essentially, it involves several translations. So we start with like parsing ECMA regex, and then translate it to alternating two-way automata, and then further to non-deterministic finite automata. Then there's a refinement loop to deal with backward references. So, and in the end, so after that, we end up with a solution to the regular expression. Okay. So it's we built on the work called Ostrich, and we extended to handle practical regular expressions. So this then can be used for finding solutions. Okay, so far so good. So yeah, we have interesting problem. We can build on SMT solving to solve it. This is the general architecture. Our scanner is scrolling around the web, interacts with the web, and when needed, it can invoke an SMT solver and get solutions from it. In a bit more detail, so this is kind of the diagram that we follow with the kind of numbers corresponding to the sequence here. So yeah, the crawler interacts with the web, finds a form. Okay, the form sends the input pattern this. Okay, we send it here. Here we have a validation controller that extracts from the web page what are the regular expressions used in the validation, and sends it to a witness controller. So witness controller, depending if we're in a exploration mode or attack mode, so we might want to generate payload and add it to the regular expression that we have in mind, and then send it to the SMT solver. Okay, this works through the regular expression, gives us a solution. So in this case, it's a solution that includes a payload for success, sends it back to crawler, and then the crawler can use the input when submitting the form. Okay, so that's the idea. As I mentioned, we build on Ostrich. We need to extend it to handle regular expressions. And for the crawling part, it's the Black Widow crawler, which I mentioned combines the benefits of the previous crawlers. So that's very good, so we can use it here. Okay, so I mentioned HTML5 validation. So that's one of the ways in which you can provide the pattern as is, and that's very convenient because we can just use it in the SMT solver. However, there are many other ways in which you can validate constraints on the web application. And here, just give you examples. In HTML5, we have all kinds of attributes, except for patterns, right? That might tell you what input type we have. So there's already an input type email, for example, that already can enforce, whether it's a valid email address or not. So that's great. There's URL, month, and so on. We can also provide min and max for constraints that we want to put on our input. So all of this is it's kind of a very nice way to enforce things on client side. What we are doing essentially, in our approach is to incorporate all these constraints. So it's not only regex, but also this. If somebody tells us, hey, here's the minimum value for a possible field, well, that's great, because then we can use it as a solution. That's perfect, right? That's what the crawler can use already. And similarly, we support all types. So for each of these types, we can have a string that satisfies that. And for pattern, we have SMT solving. As we also see in practical web applications, it's not only regular expressions, it's also JavaScript-based validation. So sometimes developer would prefer to maybe they don't know about pattern, or they can do some other kind of processing with JavaScript. So in many cases, they would end up using JavaScript functions to test the input on a regular expression. Okay, so that's one of the possibilities, and that's something we can also address in our approach, because as our scanner can rewrite code when it interacts with a web page, what we do, we can proxy the test function, and that way we're able to extract the regular expression used by JavaScript and feed it to the SMT solver. Okay, so that's great. We can not only use readily available HTML patterns, but also the ones coming from JavaScript. So yeah, this is work we need to do to kind of gather input validation constraints. Okay, so yeah, now expedition into the web. Okay, what can we find with these techniques? Okay, so for the data set, the largest archive of the web that exists is the Common Crawl archive, and that's our starting point. So we look at 20 million forms from Common Crawl. We also make sure to address all the popular pages. So look at the Tranco top 100,000 list. Also collect forms from there. Turns out that forms used a lot in the web pages, but turns out that many of them are reused. Many of the same forms are used on many pages. So in the end, we end up with around 9,000 unique valid patterns. So that's our main kind of data set. So in an ideal world, we would unleash our approach, Black Ostrich, on a website, and let's see what we find. But of course, this would be highly unethical. So this kind of active scanning that submits form, registers users, and messes around with application, that would damage application, even if it doesn't submit any payloads. Just like posting on forums and doing these arbitrary things. We don't want that, and it's not the standard in the field to do that. Therefore, to test our approach, we create a task bed where we extract a pattern. So for each of these patterns, we create a separate web page that has the same check on client side and server side, and then we check, okay, which of the scanners can get through that and which cannot. Also, we look at open source web applications that use patterns on client side and server side, and then zoom in on 3 cases where we can also compare the different scanners. All right, so how does it look in terms of coverage? So essentially, from all the patterns we discover, we can solve most of them, 99%, right? So Black Ostrich does well, 99% of the patterns are passed in the test bed. If you look at other scanners, it's about 36% on average. Some get more or less lucky. You see, like Jack doesn't even try to pass much. It focuses very much on clicks and submissions, but doesn't have much variety in terms of input that it provides. So previous combined, if is doing much worse than Black Ostrich. So this shows that the power of Black Ostrich is really useful. So to be able to pass specific input validation check really makes a difference for practical pages. So what are the examples that we can solve but others cannot? Well, these are exactly similar to the password example I showed before with look-aheads. So that's exactly the kind of patterns we see in this set. So for example, if we ask for, it has to be a digit, has to be any character between A and Z, lowercase, uppercase, and then, so all of this applied as a condition to the password string. So this is where no other scanner manages to solve the pattern, right? So they're not aware of requirements on the input. Even much simpler patterns are out of reach for the existing scanners. So, we just ask for, can you have 16 input of exactly 16 digits? Well, in the libraries that the other scanners use, they don't happen to have that input. Okay, so out of luck. And yeah, other kind of constraints, yeah, like 6, yeah. So that's where we can really show off that we are better than state of the art. The same thing for alternative patterns. So if there's some kind of range of years or some kind of strings and alphabets that other scanners don't typically cover, then for us it's super easy, just extract from the regex. Same thing for expected phone numbers. Like if you constrain by country, well, I mean, then only we can solve that. So we could ask, okay, yeah, this focus on patterns, but what if these patterns are used like only on one page, right? What is the kind of practical impact here? Remember that I mentioned that many of the patterns, they're used on many pages, on many internet domains. Therefore, we do another experiment and kind of do like weighted comparison where essentially we look at how many domains where a scanner solves all patterns. Okay, now we can have, yeah, a pattern that's very popular. That'll give us a lot of score here. Again, we solve most patterns, 99.9% for the domains here. And then, yeah, we improve coverage on 13,000 domains. Okay, so yeah, even this way, we kind of doing quite well. Okay, so another way to kind of slice and dice the result is to look at unique coverage. So essentially, yeah, what you see here is that if you look at this cell, for example, then 6,000 patterns is something that Black Ostrich can solve, but any other state cannot, right? So this is kind of, yeah, head-to-head comparison between all scanners. So you see that, yeah, in the row for Black Ostrich, there is a lot of domination. And then if you look at the column from Black Ostrich, so this is what we cannot solve, but others can. There we find some, yeah, interesting coordinate cases. So, for example, one was with, you know, some untypable characters. So at the moment, yeah, so Black Ostrich kind of emulates the user and it types various characters that are used. But some of the constraints were on, for example, delete character, which we cannot type in, right? So that's why some of the other scanners were able to solve it, but we didn't. But yeah, you see it's quite a few of those. Okay, what about cross-site scripting vulnerabilities? So I mentioned that not only coverage that we're interested in, but also how often we can actually find problems that where forms can be directly attackable with payload. So again, we see that so Black Ostrich identifies quite a lot of vulnerabilities. If we take the average, we go improve by 52% of the average. It turns out that the other scanners can only pass very simple patterns. And there are also some differences in what the other scanners consider to be a payload for attack. For us, we actually want the full payload to be present, you know, script, alert, script, so which is a bit longer. So for enemy of the state, they just put a bunch of characters and they check, okay, will we pass or not? And if we pass, then it's an attack, right? So it's quite optimistic way of considering what actually is a proof of XSS. And for ZAP also, yeah, it's only a particular kind of payload. So yeah, therefore, yeah, what we see here, yeah, I mean, some of the other scanners, they do well, but, you know, for the notion of XSS that they use, which is more lenient than what we use. Okay, so that's interesting. And overall, it shows also the state of the art that, yeah, many of the patterns do allow XSS, right? So lots of email patterns are insecure. Some examples that only Black Ostrich detects as cross-site scripting. So yeah, here's this email example that we can handle, right? So this is a typical example of, you know, slightly more specific constraint than regular constraint. Okay, if a string ends with France, then no other scanner has that in their library, right? It's quite specific. So only Black Ostrich can figure it out from the regular expression. And the same thing for, only 160 characters. Yeah, only Black Ostrich can find attacks with that length. Yeah, and here again the heat map showing that there are many of the vulnerabilities we find that nobody else finds, in head-to-head, and there are some that others find but we don't, and that's primarily with this lenient interpretation of what constitutes an attack. So no surprise there. Okay, so we'll look at open source applications. So so I mentioned that this is intended to be kind of black box technology, but everything is about how much code coverage actually gain, right? Therefore, it's interesting to look at open source applications and see how far we can get there. So we identify 3 applications that use both client-side, server-side validation. First one is Alex, uses Spring MVC, which makes validations consistent on server and client side. It has the, kind of when you create a new project, you provide URL, and it's validated against a pattern. And that's, that's used on both client side and server side. Essentially, if we compare between different scanners, we can find 25 different URL paths where others can, Black Widow can only find 9, and the other scanners get stuck even at login page already because they cannot get this one right. Okay, so that gives us quite a boost of coverage. Next application is Helping Hands, where everything is about kind of phone number that needs to be entered in login, and that's where everybody can get stuck. But we extract regex and successfully register. The third application is called Opera DNS UI for managing DNS records. So, and as such, it uses some very complex regular expressions. So like, here's an example for one of those. Right, so I mean, there's no way, just by guessing, we can provide input that would match that. So it's not surprising that only Black Ostrich manages to submit a record that satisfies this pattern. Okay, so remember we discussed that client-side validation can be done in different ways. One is by patterns, another way is by JavaScript. And therefore, what part of our evaluation is to see, okay, how often can we pass validation on top websites independently of which type of validation they use. Okay, so we look at top 100 websites that use input validation. Okay, then do some crawling, extract all patterns. Turns out that JavaScript test is used quite a lot in practice, right? Much more than the pattern. Okay, so that's interesting. So our instrumentation approach, therefore, is very useful for that. Sometimes match is used. In 3 websites, it's a pattern that is used. So the challenge with JavaScript validation is that sometimes, it's not, JavaScript check is not implemented by a pattern, but by some other JavaScript primitive. Okay, in this case, like length is 10. And also sometimes JavaScript is kind of split, and like different parts of JavaScript do different kind of validation, right? So it's much more difficult to collect all constraints. Still, the results are overall quite optimistic. So in 86% of the cases, we can actually support the validations used in those pages. Okay, so Tranco list is a typical list that is used. Popularity on web pages. So what researchers use to rank popularity of web pages in the wild. Okay, so a bit of demo, right? So it's going to go real fast because Black Ostrich is much faster than humans, and I didn't slow it down. So, but it will be a useful thing to see. On the left, web application. On the right, interaction with the constraint solver. And essentially, what you see here, Black Ostrich tries to register first. It succeeds, very quickly to register a user, and now it tries to kind of explore more of the application and finds update profile URL. Then it tries to find different paths, and after that it tries different attacks. Right, these are the different phases. And then you see here, like every now and then, it finds a regular expression in an input validation. For example, for the name here, right? And then it asks for the the input and gets an input from the SMQ solver. So yeah, and then it uses the input in the crawling. So yeah, these are the phases, and essentially, yeah, turns out that we found vulnerability in this demo. Okay, that's good. And then yeah, this is asking to solve this, and this is the solution. So this is kind of Ostrich returns in a bit cryptic way, but this is the solution to this RegEx. So that shows that essentially, yeah, we support extracting this kind of constraints, provide solutions for that. We find when injection tokens, where do they show up in the application? So here we update profile and it shows up later on list of users. That's something that we're capable of tracking. And so this is, yeah, with cryptic output of the tool, but you see basically some payloads for process scripting actually worked out. And so when we inject them in one place, it's reflected in a different place. Therefore, we have an injection that we can find this way. Excellent. So one of the kind of fascinating things that came out in this study is in particular having to do with email. And that's why, so in the rest of the talk, I'll talk more about email patterns. Okay, this is a really amazing things that's happening with them. So first of all, why is it interesting? Well, it's quite an active area of hackers, where hackers kind of make exploits. And this is one of the hackers called Inti, who is kind of boasting a bit, how he managed to get $75,000 just hacking, this kind of email vulnerabilities. Okay, so yeah, these attacks are practical. He mentions, Gmail, attacking Gmail and so on. So they're out in the wild. And well, these attacks are essentially, yeah, exactly with the payloads that I discussed. You try to match against email, but then you have some script in it, right? So this is one of his attacks. So yeah, let's see if we can do a small demo of a web page. So I need to reshare, I guess. Let me. Okay, new share. So let me try and show that. Just to show that, in the wild, it's super common to have those stop share and then share desktop. Okay, so let's hope it works. Okay, this is one of the pages found in our crawl. Okay, so yeah, I'm trusting this audience not to push this further. Okay, so we all signed ethical agreement, right? Okay, but this is one of the many examples what happens on the web. Okay, so here we have a bunch of input in the form. So let me enter some data here. First name, yeah, it should be there. Last name, and then email. So let me just try to enter some arbitrary input, okay, and submit the form. Okay, you see that the web page has client-side validation. It tells me, please match, input should match the format, okay? What's the format? Well, I can look at the source of the application. Okay, let's see if we can find that. Somewhere here, right? Okay, yes. Okay, this is the interesting part. This is exactly what I showed before, the pattern attribute. And the pattern is this one. So this is quite liberal, right? So if an attacker would want to exploit this, then it will be sufficient to do something like this, right? And then, so we try submitting. Now, so we see that it accepted this input because it moved on to the next field. It's happy with the email, okay? And then, yeah, you saw the pattern, it's liberal. So then the attacker might push it further and provide a payload, right? And then like this. I guess I'm missing something. Right. So yeah, so it's accepted. And that's so an example of being very liberal in regular expressions. Okay, so let's go back to the application. So obviously, yeah, what we saw is not a safe regular expression. Okay, and yeah, this is the kind of payload that we've tried. So that leads to interesting questions about this kind of emails. Okay, so how come that we have all those insecure validations for email? And is there a standard to support this? In fact, there is a standard. It's called IETF Internet Standard that tells exactly about how an email address looks like. Unfortunately, nobody really understands what it says, and there's no, compact way of describing what it does. Okay, so and it's too permissive because, for example, it allows quotes. So this email is a perfectly valid email against this standard. Okay, so yeah, so clearly the standard was maybe before the days of cross-site scripting, so it's way too permissive. So yeah, what should we use then if the standard even is not so secure? Well, in fact, there is something called MDN email standard that's supported by browsers, and essentially, if you provide type input email, that's what will be enforced. Okay, so this is the regular expression. This is the diagram, right? So basically, yeah, a few characters before at, and then some constraints. What can come later on? There are some length constraints on the different parts. So yeah, it's more reasonable and it doesn't allow angle brackets, for example. Okay, so that's good. However, if you look at our data set and see what's used in the wild, somehow we find a lot of that kind of crazy implementations and inconsistencies, which is very far from this standard, right? So, okay, here's one example, right? What is we found? Yeah, I mean, it's completely arbitrary, right? I mean, it's okay. It looks at it uses positive look ahead, and it looks at up to 64 characters in the beginning, and then there's some other constraints. So it's not quite consistent with what yeah, MDN, for example, specifies. So yeah, that's interesting. And in our study, we looked at yeah, we looked more about these consistency questions. So we have the patterns in the data set. We select those that have to do with email, right, by name or ID containing email. That way we extract 825 email patterns. First question we ask is, okay, so yeah, what about patterns that are weaker than MDN in the sense of, being outside, having some strings that are accepted and containing script, right? So how many patterns are attackable, essentially? Turns out that 26% of the patterns are attackable. They can contain script. Okay. So inconsistency goes both ways. So our next question is, see how many patterns are stronger than MDN in some cases, right? And then we look at, okay, what are these expressions that are stricter? So there's some strings that are accepted by MDN, but not by those patterns. Turns out that 90%. So in 90% of the cases, actually, the patterns from the data set are stronger on some strings. And these are examples. So just the fact that you demand a dot after the at, that already is more constraining than MDN, because in MDN you can have username at localhost without any dots. Well, yeah, if you ask for a dot, then you're immediately more stricter. And then we found on many pages, we found this example that essentially you register your email and it accepts an email, except that it comes from one of these free email providers, right? So it's something from the wild, and clearly this is stricter than MDN standard. Okay, so yeah, the inconsistency goes both ways. And the final email study is reusing. Yeah, so I mentioned that it's good for client-side validation and server-side validation to be aligned. But the tricky thing is that if you reuse the expression one-to-one, then actually you open up for insecurities, because on the client side, you can automatically have full matching. So it should be like from beginning to end. It's a full string that should match because of HTML standard. On server side, so it depends on the engine. And many of the engines, they're more liberal, and they say a substring needs to be matched, right? You don't need to match the full string. If you find a pattern in a substring, that's fine. And that's, super liberal, right? So if you reuse the same pattern from here in the server side, then you potentially open up for insecurity, because now, you're not explicit about beginning and end of a match. So with this experiment, we look, what if we just reuse, in how many cases will be insecure? It turns out 60%, right? And we find an example in the wild that kind of recommends reusing the pattern without making it full input pattern, right? So it's, if people look for, it's quite common to find, to basically be confused about this and reuse the pattern as it is. Okay, so that brings me to the conclusions. So essentially, hope you enjoyed this expedition into pushing the boundary of deeper crawling of the web. Thanks to string constraint solving capabilities, we are able to get past input validation checks, giving us increased coverage, giving us increased attack detection. And somewhat entertaining for case study of email shows that even though there are perfectly fine mechanisms available for validating email, and even there's an email type, so you don't need to have any regex, you just say type email, and then this regex will be used by the browser automatically. Still, developers have a lot of on implementations with inconsistencies both ways, so that 26% of validation patterns are actually susceptible to cross-scripting. Thanks very much.
Thank you.